Okay, let's start. Good afternoon. It's now 2 o'clock here in Taiwan, and perhaps some other time in other places. We welcome you to this online lecture to be given by Professor Charles Lin of the National Cheng University, Taiwan. And Professor Charles Lin, he is now the director of the Hsia Space Science and Technology Center of the National Cheng University. And he's also a distinguished professor at the Department of Earth Science at the same university. He got his PhD from the Space Science Institute of National Central University under a joint agreement with NCKU in America. And afterward, he spent some time doing his postdoc and before returning to National Central University, and all the time spending there. And the important thing is that Professor Lin, he is a leading expert in the field of GNSSRO and even GNSR, which is important for Taiwan because Taiwan, as you know, we have a sequence of such a GNSSRO satellite. In future, this line of investigation will be expanded, and so there are many applications to this technology, this technique, and the tsunami early warning is perhaps one of them. So we are very happy to be able to invite Professor Lin to give this talk. The title of the talk is called Capturing the Tsunami and Volcano Signals in Space, GNSSR Detection of the Ionosphere Disturbances. Okay, Professor Lin, please.
Okay, thank you so much. I hope this time there's no technical issue for that. I'm sorry for the previous talk was canceled because of I couldn't figure out how to share the screen. Okay, so this is a collaborative work from many scientists from NCKU and also from Tiger Liu and Cheng from NCKU, and also two important partners from the Goddard Space Flight Center of NASA, Mingyang Zhou and Jia Yue. Mingyang has previously spoken at this seminar series. So today I will mainly in the introduction given by the Professor Yip that I mentioned about the GNSS-RO over the Formosec 3 Cosmic 1 or Formosec 7 Cosmic 2, and also Triton GNSS reflectometry. But before that, beforehand, I will show the majority of the results are based on the ground-based GNSS receivers. The idea is that because we first have done this back in 1999 when there's a huge earthquake called Chichi earthquake occurred in Taiwan, and then we for the earthquake produce of a signal in the space, we did that for the Chichi earthquake in 1999. For the tsunami, the first try for Professor Tiger Liu and me was doing after the 2004 Sumatra earthquake, and that really gave us a lot of hope to do this tsunami signal in ionosphere. So I would just quickly mention how this was done using the ground-based GNSS observations. So suppose when you have this GNSS positioning system, that the idea is that this GNSS satellite will transmit radios with code. That code is already broadcast or published to all the users, so that if somebody build a receiver, they can replicate exactly the same coding in their receiver. So receiver will generate a replica code, and then transmitter will transmit the code. And when the code was transmitted from the GNSS satellite and received by the ground station, there's a time difference. Based on that time difference, multiplied by the speed of light in the vacuum, you can roughly get this distance between the satellite and the ground station. It is all idea that the median in between the satellite and the receiver are in vacuum, then that distance will be the exact distance. However, the reality is that they are ionosphere plasma and the atmosphere reflectivities. So really the actual velocity of the line, speed of light is smaller than the speed of light in the vacuum. So when we multiply the speed of light in vacuum to the time delay, we call it as a pseudo range. Okay, anyway, before we talk about how the pseudo range transfer into a real range, I'll just mention that if everything is perfect, pseudo range is the exact real range. The idea for the positioning is that you know exactly what the GPS, the position of a GPS satellite or GNSS satellite. So it's the XYZ with a superscript of IJK. I'm sorry, this is not. Oh yeah, this I is the number, the number of the satellites. For example, satellite number 1, satellite number 10. Okay, you know the exact position of the satellite. You don't know exact position XYZ of your station, but you know XYZ of satellite plus you know the distance. So you can easily write one equation to describe that. Then if you collect 3 satellites, if there's no clock bias, you can collect 3 satellites and you have a 3 equation that can solve the 3 unknown XYZ of your ground station. So that's the principle of positioning. Okay. Reality, what I mentioned is that the delay, the range is what we call is a pseudo range. That means it's a actual range plus the delay caused by the ionosphere in the dry air and the wet air. So we can do the other way around by if you know the exact position of your ground receiver. And of course, you know the XYZ of a satellite because it's always broadcasting out from the satellite. Then you can get a delay coming from this ionosphere and dry and wet air. And if you use a dual frequency to eliminate the atmosphere perturbations, which is non-dispersive, you can do the subtraction of the two frequency observation from 2 frequencies. Then what you get is really the ionosphere delay. So that's the idea how we get this ionosphere delay. And ionosphere delay can change into the ionosphere total electron content. That means the electron density integration along the ray path. And in order to have a comparison of a horizontal gradient of an ionosphere, we normally convert this slant line of sight total electron content into this vertical total electron content. Okay, with some simple technique, we can convert that to a vertical. So the actual product is a vertical total electron content or VTEC. Okay, and there are a lot of opportunity of a signal from the ground-based stations because human being has built several hundreds of the I should say thousands of a ground-based station for seismology observation or any tectonic displacement rate observation using this ground-based GNSS receiver, and those receivers, all of them have a known position, so we can use their data to calculate this vertical total electron content whenever at the location when you have the ground-based station. So at the time I show in this figure, maybe there are 3,000. Nowadays it can be 6,000 or even more that can be obtained publicly. Okay, that's the idea of that's how we have that measurement. If I go back to look at here, the way I'm going to talk about this is the way we treat this system is like assuming this is like a passive radar. Passive radar means the transmitter is from the space, from the GNSS satellite, and receivers are on the ground. And any vibration, any variations in the ionosphere producing the Doppler shift in the signal. So if you can do some high pass filtering or the other band pass filtering of this vertical total electron content, then you can get this variation in the ionosphere. And that's the key for us to obtain this ionosphere perturbation due to this earthquake, tsunami, and volcano. So back in the day, this term was coined by Tiger. He wanted to put this as a space seismometer. I want to mention this. When we did this, I was a PhD student working in UNCA with a thesis on magnetic storm effect in ionosphere. So I purely do this. I purely did this with Tiger for fun. We just do this for fun, and it's easy because you can really get the ground-based GNSS data publicly, and then we have a program to handle the GPS observation data, and then after obtaining the TEC, we can just apply the filter, and then you can just find the stations around the epicenter, around the region of interest, and then you can do a bandpass filtering over TEC. Then you can get what I'm just about to show you. Okay, so the idea is that if there's any earthquake producing the wave that's capable of propagating to the space, to the ionosphere, then it's possible we can detect it through these TEC variations. Okay. So this is an example from this Chichi earthquake. I'm sorry, I maybe missed one PowerPoint slide. Oh, it's gone. Okay, it's okay. So it's an example that we can see from this Chichi earthquake. These blue triangles are the stations, and the red dots are the sub-ionosphere point, the location where we have this VTEC, the geophysical location of these VTECs. So these are the VTECs and the raw data. So at one time you can see many different TEC. That means you see different satellite in different angle, zenith angle from the station. Okay. So here one time you can see maybe roughly 8 or 10 lines, and those are observation from maybe 10 different GPS satellites. And I want you to make attention that on this red circle area, you can see there's a geek in this area in the VTEC, in the TEC. So if we apply the high pass filter, so simply apply the high pass filter, this is what you got. Here, these are actually the N shape of the perturbations, and it has a time sequential. That means it's likely something is propagating from one location, one station to the other. So we arrange this. So if we count that, okay, these starting point of the N shape represented by these red dots, and find the spatial location of them, and find the distance between them and the epicenter, plotting in the y-axis, and the horizontal axis is the time. Then you can see that these distance in these red dots become these red triangles. And there's a slope over there. It's roughly 1.1 kilometer per second. That's really coincided to the sound wave, acoustic wave in the ionosphere. Okay, so this was a paper. It's a Chichi earthquake paper, but it was published in JGR 2010. I will let you know why. It takes a decade to have this published, because when we first did this, nobody believed this is the earthquake effect. I mean, people would just think, oh no, this is just normal travel ionosphere disturbance, because in ionosphere there are many waves. And at the time when we did this at 1999 or 2000, roughly year 2000, people are so fascinating to a geomagnetic storm effect. And geomagnetic storm effect will produce a high energy deposition at the polar region. And that will create these atmosphere perturbations from polar region to the equator. Thereby, when that atmosphere oscillates, ionosphere will oscillate together with the atmosphere. Then there are a lot of traveling ionosphere disturbance. We call it as a TID, traveling ionosphere disturbance, TID. And when we show this to people, they say, no, this is not earthquake. This just by luck, you see the TID located or propagating nearby your earthquake site. Okay, so it's difficult to have this published at the time when after the GC earthquake. Shortly after that, it's difficult to have it published. And then we try another one. I believe this was a 2003 Hokkaido earthquake. And there's another seismologist, professor in Hokkaido University, Professor Heki. He was also doing the similar things. Okay, and we just do this event that he also we also worked on at the time. So this was a similar, but the resolution is not so good. But you can see there are spikes over here in the red circle in the TEC. So again, if we do the filtering, this time we do this bandpass filtering for this period, the 150 to 350 second period, bandpass filter. We again see this, and again we arrange them in respect to the distance to the epicenter along time. You see again 1.1 kilometer per second of the traveling velocity. Again, this is very close to the sound speed traveling in the ionosphere. Okay, so okay, I got this figure. So idea is this. I like this cartoon plot very much. It was provided by Professor Heki of the Hokkaido University. So idea is that if you have a tectonic or displacement in the plate, it will produce variations, and that will shake this ground station. But the other thing is that if it propagating, it has something disturbance propagating to ionosphere. That can propagate very quick in ionosphere, like 1.1 kilometer per second. And then when it goes to about this station, you will see the variation in the signal. I will just create the cartoon for you. The ground variation, share the receiver, perturbation to ionosphere, produce it, and then GPS signal gets shared. Okay, that's the idea of the space seismometer. Okay, then we were kind of very successful in this Chichi earthquake and the Hokkaido earthquake. Then Sumatra earthquake came. Then I remember, just tell a story. Maybe some of you have heard of this. So I was doing my thesis, as mentioned, in NCKU with a magnetic storm. But after that Sumatra earthquake, I briefly come back to Taiwan to do my visa stuff. And then Tiger called me and said, hey, let's look at this Sumatra earthquake and tsunami. I said, no, tsunami is difficult, right? You have the ocean wave on the ocean the whole time, but you never see the ocean wave produce any perturbation in ionosphere, right? So I told Tiger, forget about it. And he said, no, let's give it a try. With just only one night of work, right? We go to a laboratory, try the data for one night. If it doesn't work, forget about it. If it works, we hit a jackpot, right? So we did that, and we did hit a jackpot. So it was a very interesting evening working together to the late evening to find it out. But at the time, I like to draw your attention that at the time we don't know how the tsunami signal looked like. It definitely will not look like this. This is so easy to identify, right? It's so clear, it's an N shape. But how does that would be happen in the Sumatra earthquake? The other difficulty is this. This is the the cartoon plot based on this Sumatra earthquake and tsunami. This is the other very difficult thing, is that at the time here, I mean, you can find very limited ground-based GNSS station. You see, majority of this region is ocean and small islands, and even there are GPS stations. At the time, the data were not public available. So we're kind of like, okay, how many stations we can get? Okay, and let me just show you. We actually get roughly less than 10 stations, and from that 10 stations, we found 5 stations having the signature of the tsunami effect in the ionosphere. But I look at this blue lines over here. Here we only simply do the high pass filter, very simple high pass filter by just by doing the differential of the signal. And then we have one base is that we have one paper showing the tsunami simulation, arrival time of tsunami simulation, that this figure. So 1 hour after the tsunami occurred, 2 hours, 3 hours, 4 hours, and our stations are here. Okay, so we're kind of like, okay, suppose we should see this 4 hours data. Do we see that? And then we see this spatial, this suspicious the wavy structure, but we don't know if that's real. And then we overplot the previous day data. with this gray line, then it becomes so clear that the previous state, is kind of flat. And then here is like, it's a small square waves. That is, this, as I mentioned to you, that this is definitely very different from the earthquake signal. So we didn't know how it should look like. So we just only do that. Okay. Then we roughly find, okay, it have to be these square waves with sequentials. Not only one. If there's one, then we don't count it. So for example, here you see there's a sequential of square waves. Okay. And then later here they are square waves in the sequential. Okay, just a second. Just I need to figure out. Okay. Now, how do we know if this is real? So we apply exactly the same thing as we did before. Find out the likely starting time of this tsunami signature in the ionosphere and arrange them in distance to the distance in respect to the epicenter. And with the time, and then we plot this, the red line or the red line. I think it's a red line. Yeah, it's a triangle, right? And then again, we also plot that a theoretical tsunami propagation, a simple one with this red line. And you see there's a difference, okay? The difference over here can translate into roughly 8 minutes. Okay, 8 minutes is a magic number, okay? So just let you know that this one shows clear tsunami signal with this kind of square waves. And this paper, when we found it, we were very happy. We saw that, oh, okay, yeah, it's an 8 minute delay. When we found it, we were like, oh, man, well, before us, there was one French group, uh, Juliet, leading by one scientist from Caltech. I think her name is Juliet Archer. She published one or two papers on tsunami effect in the ionosphere GPS TEC. But the thing is that she has to use like 1,000 stations from Japan to find a coherent perturbation likely coming from the tsunami occurring from Peru, from the other side of the Pacific Ocean. So the signal already been very weak and disrupted, but she used that 1,000 station to roughly find out one coherent signal. Okay, but never been anyone who use an individual GPS receiver to find out how the wave, how the shape of the wave should be like in the TEC. I think we are the first one to figure it out. So we were very happy, and Tiger was very eager to try to write a paper for Nature, for Science, but we've been rejected the whole time, So after 2 years, we have this published in JGR. But story still continue. I will tell you the more story later on, after the Tohoku earthquake. So again, when we put together a paper, we don't want to just only show people here. We did the way that the seismologists did by finding the possible source of this ionosphere disturbance using this beamforming method. The idea is very simple, that you treat any point on the map as a possible source of the perturbation, and you calculate the arrival time based on the velocity in this slope. You know the velocity from this slope, right? So you can just roughly calculate the arrival time of the perturbations if the source is here, and the arrival time to here should be how many minutes later, okay? Then every point you do the one calculation, and every point, because we have a roughly 10 data set, like 10 data points, okay? So every point you have a 10 different arrival time, and you find the standard deviation of that arrival times. And you find a minimal standard deviation time. So the largest one is 215. So if the standard deviation is more than 200 minutes, it's unlikely that be a source, right? So we have a converged result roughly at here. The standard deviation is only 15 minutes. And it's not bad if you only have these 10 points in this wide area, and you are guessing this point, which is not very, very far from this actual epicenter. And then we saw, okay, this is a strong proof telling us these are the source from this one. But again, why our paper never been accepted? Not, we publish in JGR, not a GIL, right? Even GIL, they don't buy our story. They just saw that, there are a lot of questions. So we even been rejected by the GIL. So really, the other complaint is that there are questions that in the previous one, TCL square, people would think you just being locked when there's a TID along with your earthquake. Here, it's even more, even wider area. So, I mean, you can roughly know that. Well, people can easily question you, right? It just might happen in different ways. Even we show this, I mean, people still question. Okay. I will come back to this one later. Okay. I'm sorry. So why people are questioning us is this. If you think atmosphere is one atmosphere from the troposphere and stratosphere, mesosphere to the thermosphere, where the ionosphere is a thermosphere. And everything happen in the troposphere or lower surface atmosphere can go all the way to the thermosphere and ionosphere. That's very wrong because there are strong temperature gradient at the mesosphere, especially at the mesopoles. It's very cold, and when it comes to thermosphere, the temperature start to increase. So there's a sharp gradient in the temperature. That tells us that there a lot of turbulence occur at the mesopoles. So traditionally, although atmosphere can be one system altogether, but all the waves, perturbations, can be broken at the mesopoles because of the strong eddy and turbulence. That would destroy all the waves. So at the time, nobody really believed you can have any perturbation from the surface or go all the way to the ionosphere. I mean, even now, people are debating. People think, even now, with so many evidence, people still think, no, you cannot do that. The only possible way, I mean, some people think this way. The only possible way is that you have your wave broken and then have an energy deposition to the thermosphere and then generate a secondary wave. That's how some of the people right now still insist this should be the case. Otherwise, the atmosphere principle is not hold. Okay, so I can understand why people against us at the time. Okay, with 10 data point, I mean, how can you break this golden rule of the atmosphere? Until this time, Tohoku earthquake, this is really the game changer because it happened at a region where you have more than 1,000 stations. Remember, Julia Archer's paper was dealing with a tsunami happening in Peru, go 9,000 kilometers to Japan. So what the signal you see is very weak and it's along the coastline. But for this Tohoku earthquake, I'm going to show you, it's so clear. You see the concentric circular waves. So overplotting at the bottom is a tsunami simulation of the surface wave height. And these green and the yellow dots are the GNSS from more than 1,000 stations from Japan and 140 stations over Taiwan. And here is a movie you can show. You can see that earthquake occurred from the epicenter. There's quickly the seismic wave propagating out, already arrived Taiwan. This is maybe a ready wave. And tsunami occur. This is way high, the height of the tsunami wave. And then the fast wave becomes slower from the epicenter propagating out. And then this faster wave succeed. And then this coincided with a tsunami shape of waves propagating in the similar phase velocity with tsunami, but they have some leading in the space. You can see that here. There are some of the leading space. Okay, that means, but when you go to this Pacific Ocean, there's no station, so you don't see that. But you can see the other side. Okay, you see these circular waves. Okay, then this tsunami continues to progress, and then you have this ionosphere perturbations go a little bit faster than that. Okay. If you don't count the seismic wave at the beginning, okay, I can let it run again so that I can talk about this. So this is really the evidence is so strong for this one. Like you have this concentric shape, and along with the earthquake, and then if people talk about TIDE, right, it has to be from the polar region to the equator, and it's actually during this day there was a moderate scale of the solar magnetic storm happened at the same time. So I mean, but this evidence is so strong that nobody would say, "Oh, this is caused by the solar magnetic storm." Indeed, there was a one solar magnetic storm happened a few hours before this earthquake and tsunami. But I mean, nobody would think this is really connected to the magnetic storm. Everybody think this is relevant to this earthquake and tsunami. Then people start to believe that that this is real, you know. So for this one, we can publish this much quicker, you know. I mean, 1 or 2 months after the event, we already published a paper and been highlighted by JGR. So this is a really, I think, time that this is really the event that people start to convince that you know that you can really see the perturbation of a earthquake and tsunami in the ionosphere. Okay, and here are some snapshot of the plot, and then we can get really the phase velocity of this mega event. For this mega event, as I show you that you can have a 3 kilometer per second of a fast propagating time. This is likely the really wave, the earthquake wave. And then again, our good friend, roughly 1 kilometer per second of the perturbation, like what we saw in the Chichi earthquake and the Hokkaido earthquake. Then there's a slower one, and then there's roughly close to 200 meter per second one. These are in the very close phase velocity of an actual tsunami height. Okay. Okay, I want to show you more. This is after 10 years, we again go back to check the data. So at the time in the space, we have a formal satellite Cosmic satellite. These are radio occultation observations. But if we plot out the total electron content for before retrieval into the electron density profile, because we cannot use the retrieve electron density profile that already been processed by some mathematical method. The wavy structure can be smoothed out by the method. So we look at those raw data and then find the oscillation of it. We do see some fluctuation in altitudes. Okay, and here are the effect. Okay. Then again, this is the figure we plot 10 years later. I think this is a result published in 2020. Okay. And then you can see the tsunami wave around US, and then you see these very distinct waves in the ionosphere. And again, the waves here, and if you compare the distance, the ionosphere lead the tsunami by certain distance or certain time. But it go all the way across the Pacific Ocean. So the leading time is kind of a certain, roughly, I think it's roughly 1 hour. No longer than 1 hour. That's roughly okay. The idea. Again, you can see the radio occultation. But for occultation, the difficulty is this. Occultation are radio occultations in the horizontal slice. So if some occultations go horizontally, so for example here, if the occultation has a geometry like this number 1, it's difficult to see because it covers that. If you have a occultation goes like in different geometry, some geometry is very good to detecting this wave, some are not. So occultation sometimes is difficult because it covers such a wide area in the horizontal distance. Okay. Yeah. Now, I want to find a similar feature between the Chichi earthquake and Tohoku earthquake. and how the tsunami signal should be compared to Sumatra earthquake and this Tohoku earthquake. So again, if you look at this Chichi earthquake, you find only these N-shaped waves. Do we see these N-shaped waves in the Tohoku earthquake? Yes, we did. Here you see these N-shaped waves. Here are all these earthquake waves. Okay, but later we find our very good friend, this sequential of square waves. These are the tsunami waves, as what we saw from the Sumatra earthquake. Okay, here you see the spike, and these are not the tsunami wave. These are the earthquake wave. This guy or this guy, you see the square wave and the sequential many and the longer wavelengths or longer time period. These are the tsunami wave. It's so similar to this Sumatra earthquake and tsunami or Sumatra earthquake. I mean, so when I first look at this Tohoku earthquake, I look at this raw data, I was like, oh, yes, this is for sure the tsunami wave. I mean, I saw this like, 7 years ago, or 6, 7 years ago. This is the one that we saw in the Sumatra. Okay. Now I want to talk about this. Is this? If we look at this 9 plots of the data without plotting them into horizontal spatials, I'm telling you, this is an earthquake wave, and this is tsunami wave. I mean, some of you might still be questioning, right? There are so many perturbations in the ionosphere. How are you sure? So our previous study for the solar magnetic zone now come to the role because we have been studying this so much that we know a lot of signal from those solar magnetic zone effect. For example, for a solar flare, for this solar flare event, we use many stations in Europe, and all the stations show simultaneously spike with no time delay from stations because all the stations at the bayside view the sun at the location of a solar flare, and then you will see this kind of a structure. It's increased all of a sudden altogether. There's no time delay. This is a solar flare effect. This is not an earthquake and tsunami effect. Okay. How about the solar magnetic storm? This is the DST, the indicator of the storm. The rain phase occur at the minimum of the DST and recovery phase. Okay. Then what's the traveling ionosphere disturbance produced by the solar magnetic storm? That would be this guy. The whole Japan become red color and the blue color because the solar magnetic zone effect creates something with such a long wavelength, 1,000-kilometer wavelength, so that it's much larger than those tsunami earthquake wave as you've seen for those Tohoku earthquake event. So this is just one example of it. Okay. How about the quiet time? In Japan, people always see this medium scale TID that happened in the solstice, and it propagating along the shell of Japan for some physical reason. It's a coupling protein instability in the ES layer, but I'm not going to talk about that. But we know it has a special direction and propagation direction. It has a special direction for the wavefront and the propagation direction. Okay, then it also goes very slow, 120, roughly 120 meters per second. And then we know this is a daily MSCID. This is no way the earthquake and tsunami effect. Okay, so we know how to distinguish the signal because we have used this GPS TEC observation to do many things, and then so that their character are really different. Okay. So this is also the 2020 paper. Was an interview by a new scientist, I think. We published this in Space Weather, AGU Journal Space Weather, and it was an interview by a new scientist. The thing is this, you see the tsunami produce a perturbation in US already. This is almost more than 10 hours after the tsunami. But we still see this kind of waves likely the tsunami effect in Japan, over Japan. This is not MSCID. This is not a stone effect. You see this, it's like there's big source in the center and they produce a wave in the US and in Japan, right? Try to put together this tsunami simulation over here as a comparison, but it's not easy to see. Let's look at the next figure. Here is a tsunami simulation on the upper right. And then if you hit the movie to run, you will see tsunami wave go out. And then when he hit the ocean bottom topology, the tsunami wave refract back. Okay, there's a reflection of tsunami wave. You can see. So you see this first wave come to here, hit the topology of the bottom ocean, and the wave come back. There's a wave coming back. Do you see that? There's a ripple coming out from here and going toward Japan. And that's really what we see here. You know, what we see here is the reflecting tsunami wave coming back to Japan. And Ionosphere can show this. And then there's the MSCID occur. But before MSCID occur, you see these are the reflecting tsunami waves. So we were so shocked because it's so sensitive. We found out ionosphere is so sensitive. If the ocean wave is so coherent, and then ionosphere response can be seen so easy. Okay. Yeah. Okay. So I before this I will go back to the cartoon movie I skip here. The concept of tsunami warning using GNSS-TEC. So there are two things we can think about. First is that if there's a tsunami occur here, produce a wave to the ionosphere, and when it arrives here, and the line of sight from GPS to a ground station can detect it. That's the first thing. Second thing is this: tsunami goes 200 meters per second, okay, and then perturbation waves, sound wave goes 800 meters to 1 kilometer per second. So it goes 4 to 5 times faster than the speed at the surface. So it goes faster to here in the ionosphere. And also you have that sign can be, close to crossing the ionosphere at offshore, okay? But the only weakness is this: it takes 8 minutes from the surface to propagate into ionosphere. So I will show you this movie, the concept why we can observe the tsunami signature in ionosphere earlier than the actual arrival of the tsunami itself. I'm sorry. Yeah. So when GPS satellite come, tsunami, we change that into the, 720 kilometers per hour. And then this tsunami perturbation go much faster, 4 to 5 times faster, and then producing this ionosphere disturbance, and then dioxide transpass into this region, and you can detect it. So this is the idea that if you use ground-based stations around the coast, and you are able to see this tsunami signature in the ionosphere earlier than the actual arrival of the tsunami. Because of this, okay, this is using the ground-based one. This is to use the ground-based one. Okay, so why we think the whole system looked like this is a recent 5 years ago the simulation done by Emory-Riddle University. There's a simulation group in the Emory-Riddle University in US. Located, the university is at Florida. They do this simulation, and they show that this is a neutral atmosphere oscillation. But of course, when you see the neutral atmosphere oscillation like this, ionosphere will be affected by that, because the majority of the in the ionosphere height, thermosphere density, neutral density is still 1,000 to 100,000 more than the ion density. So when you have this oscillation for neutral atmosphere, ionosphere will oscillate at the same time. So this is how we call the acoustic gravity wave. When there's an explosive event occur, so you have this leading wave is an acoustic wave, it's like a nuclear weapon. You see that from the movie where when there's a bomb drop, you see there's a bow wave, and you see a shape of an acoustic wave, and then the phase and group velocity goes up in the same direction. Okay, but when you go up and are propagating out, it has some limitation to go up. Okay, then later when you go further away from the center, you will see this downward phase velocity. And this is really the property of a gravity wave. So you have this phase velocity go down, and then this group velocity, or the actual energy goes up. So this is a gravity wave, and this is acoustic wave. This is how we call it acoustic gravity wave. And in this simulation, they also capture this is a static gravity wave. So there's a gravity wave being transmitted along this, around this mesopoles and thermosphere boundary. Okay, that's a much smaller scale. And then I want to draw your attention this: why in the U.S.? So when the earthquake tsunami happened in Japan, right? You will see the acoustic wave nearby Japan area all the way to Taiwan. You can see that. But after 1,000 to 2,000 kilometer away, what's that? Is this gravity wave. Okay, so when it comes to US for the Tohoku earthquake, you don't see the acoustic wave anymore. What you see is really this gravity wave. But this gravity wave has this kind of extending shape. So it still goes ahead of this actual tsunami. So that's why when I show the observation in US, the TIDs in ionosphere still lead the actual tsunami. It's because it has this kind of extended shape. And that's the key for the tsunami warning, because you have to have something go faster in ionosphere. Okay. Traditionally, people think gravity wave travel slow. So traditionally, before we did this, before Tiger and I did all this, people think tsunami, earthquake. Well, people believe there's a effect over there. No, most of people think. Well, I mean, the people among people who believe this is a effect. Okay, they will think ionosphere delay. Oh, I'm sorry, ionosphere disturbance delay is a delay from the actual tsunami. So they think tsunami still go faster, ionosphere behind. But I mean, based on the result from Tiger and myself, we don't see that. We always see the perturbation in the ionosphere go faster than the tsunami itself. And then this simulation really answers that, because you see this, even the gravity wave has an extended spatial coverage ahead of the tsunami. Okay, so this really help us to, answer all the questions we have. Really, this is not a traditional thought that the gravity, even there's a gravity wave propagating to the ionosphere, it lag behind the tsunami, which is wrong, because you see this one, it's leading. Okay, I just want to make this so clear. I'm sorry, I have been spending too much time on that. I'll quickly go to this Tonga volcano. And all of us, I think most of us know this, it produced some visible perturbations. And I think this one is interesting. People 9,000 kilometers away still hear the volcano erupting. I can say it may be the sound wave being carried by this. So I'm treating this as a boat carrying all the disturbance propagating out. So for that Tonga volcano, it's likely this boat carrying all the sound wave of the volcano and go all the way exploding out. That's why several hours later, people in Alaska hear the volcano voice, 9,000 kilometers away from there. Okay. Yeah. So this is an atmosphere pressure perturbation of it. You can see that Tonga is so, Tonga is so prominent because people can see this by the bare eye, and then pressure difference can be seen in Japan, Taiwan. How about in ionosphere? Let's see. This is a paper by Wright in Nature. They show this is gravity wave in the middle hemisphere. This is from Sumi MPP, day-night band. This is from GPS TEC, from UK group. And then we all know this Tonga volcano produced this LEM wave. That's like the constant vertical wave in the troposphere propagating outward from the volcano at a fixed velocity of 300 meters per second. Okay, so we quickly to use this GPS TC to look at again, and we compare with this pressure plot from this Himawari satellite. And you can see that if we look at Japan, okay, this actual LEM wave from the volcano arrived Japan around 11 UT. Okay, and I will run this again to show you that you see, so we plot this Australia TEC perturbation and Australia and Japan TEC perturbation, and you see now there's a wave going this direction, going from the east to west, not to the north. You see here, the LEM wave goes to Japan in the north, but when we see perturbation, I'll just show again. Here, it goes from east to west. It's not the north, okay? And second is this is way too early. We see this at 7:30 UT, and I mean the actual LEM wave arrived 11 UT. So what do we see over here? Okay, I'm going to show you here. So the way we suspect this is coming from the conjugate effect from the magnetic field. That is, when the perturbation go to Australia, it will oscillate the magnetic field in Australia. And then so that the opposite side, the conjugate side, northern hemisphere side of Australia, which is Japan, can feel the oscillation of the magnetic field. And that oscillation is reflecting on the GPS TEC. So the way to prove this hypothesis is to plot the Australia data along the magnetic field line projected to the northern hemisphere, and project the Japan data to the southern hemisphere with different color. Okay, so this green color is really the stations from Japan or stations from Australia. This golden color or brown colors are the conjugate one. Okay, then we round it. This is a short wavelength one. This is a long wavelength one. This is everything. Okay, let's take a look. The movie. So when the volcanoes start to occur, and then wave comes out with a fixed 300 meters per second of velocity, and when it comes out, it will ride New Zealand, and you see this TID in the New Zealand, very clear. Okay, and then when you arrive Australia, you see the same thing. And now I want you to notice this. Perturbation goes to Australia, goes to east to west. Now look at the northern hemisphere. You see the connecting wave goes from east to west. So really, this is the conjugate effect. And it arrives around 7:30 to 8 UT. Then you see this one. And then when it goes to around 11 UT, when the actual LEM wave arrives, the perturbation changing from east to west to the northwest. Now it changes direction to northwest. Okay, so it's really, so we now know that, okay, for the tsunami, we can see the perturbation in the ionosphere. We can see the reflecting tsunami in the Tohoku earthquake in the previous plot. And now the conjugate along the magnetic field line can also give you earlier times heading to the actual arrival of the perturbation by the volcano, Okay, so this is a conjugate effect, okay? Yeah, you have perturbation in one hemisphere. Simulation show that in the opposite hemisphere, you can have some perturbations, although it's weaker compared to the original hemisphere. So we plot the same thing. This was a GIL 2022 paper. So actually we have this published at the same time. You see there's a TID occur here, and then in the opposite hemisphere, it's actually here. The conjugate of this point is to here, and we can see that. Okay, so here, just let you see the Tonga again globally. So we plot everything like the way we arrange the data, like the previous plot, but change it to global. Now you see so clearly, north to south hemisphere symmetrically show that then we arrive changing the direction. And then later in US, you can see a perturbation. If I plot in the other view angle, then you can see the perturbation in Europe, in Africa, in South America and US. You can see that. Okay. Yeah. So I like this simulation a lot by simulation by Shinagawa and Miyoshi EPS 2024. This is actually a feature paper of the EPS. They do the simulation, and then there's a dam wave here go to the lower atmosphere, and then it will trigger the thermosphere gravity wave. And you see the dam waves here, and the dam waves here and here, and the gravity wave is sent it out. For their simulations, even 5,000 kilometers ahead of the source of the dam wave, and here are the snapshot of it. You see there are a lot of resemblance to the simulation by Internet or 2020. Okay, so really we think that the mechanism probably the same. You have any perturbation from troposphere, mesosphere, I'm sorry, stratosphere, and the lower mesosphere. That if for some certain physical criteria, it can produce a gravity wave at the thermosphere, and that would affect the ionosphere. Because the thermosphere neutral density cannot be observed, so people can only refer this from this ionosphere observation. You can only observe ionosphere variation, then you refer what might happen in the thermosphere. For the thermosphere, you can do the simulation, but they're actually very limited observation from there. And a similar simulation was done by NCKU by Handy Liu. They published this. They published this in GIO 2023. Again, you see this is a dam wave. Okay, go. It's like a horizontal, vertically identical, and then what's triggered above is like it sent it out of the perturbation. Okay, then these are the gravity wave signature, and then if they plot out what the feature only at the thermosphere is a concentric one. Okay, so all three simulations show similar feature. That is, any perturbation below produce a gravity wave in thermosphere has some leading time to the surface wave. Okay. I just also want to show you that both Tohoku earthquake and Tonga volcano create the ionosphere density hole. This was published by Shinagawa and also from the postdoc Zhongmin Choi from my group. This is for the Tohoku earthquake. There's a hole. Okay. For the Tonga volcano, we use Formosa 7 Cosmic 2. We also observe a great hole. And because we have a vertical electron density distribution, we can actually guess what might be the cause of it. This hole is much greater than the one at Tohoku earthquake. Tohoku earthquake, this one less than, the scale size is roughly 500, 600 kilometers. And it lasts for like 1 hour. For the Tonga, it lasts for several hours. And then the extension is much larger. But we do see this kind of hole, and data is connected to a background ionosphere. Okay, I think I'm about to conclude my presentation. I've been speaking too long. So the other challenge is that there are also other perturbations that can produce a concentric wave. For example, this typhoon, and for example, this solar eclipse. But I want to mention that solar eclipse one is very weak. So I mean, tsunami and earthquake effect can overpower eclipse one with no question. For the typhoon, probably in the comparable magnitude. Also, the rocket launch can produce some. But I'm not going to talk about that. But also for the rocket launch, we know the trajectory of a rocket, so we can easily rule out the effect from the rocket. So I mean, in the certain scale of the earthquake, we can really observe this earthquake and tsunami effect in the ionosphere. So this is my summary. I would just let you read this through because it just only summarizes what I've been presenting. Thank you for your time. If there's still time, I can take question if there's any. Thank you.
Okay, Charles, thank you very much for a very interesting talk and very informative. And you can see from the chat box, there's a question from Matthew Moses.
Okay.
Moses, can you read your question or just ask the question?
Oh, what determined the bandpass filter? Yeah. Okay. Okay. Yeah. Good question. Very good question. So at the beginning, we were just follow seismologists. Seismologists, they found out from the seismometer, the radio wave and also the some of the earthquake wave has a frequency of 100, have a period of 150 to 300 meters per second. I'm sorry, 150 to 300 seconds. So at the beginning, when I showed that the bandpass filter of 150 to 300 seconds was based on the seismologist observation in the seismometer. Um, it's actually, we found that if we want to detect a tsunami, maybe for the gravity wave, you have to have the period longer than 10 minutes. For the acoustic wave, maybe 2 to 6 minutes are good bandpass filter to detect the acoustic wave. For gravity wave, 10 to 30 minutes of the bandpass filter will be good. So I hope this answers the question.
Any other questions? I have a question, Charles.
Yes.
With this kind of tsunami-induced ionospheric traveling disturbances, you said that the signature runs ahead of the tsunamis by
Yes.
an hour or so. Would that be useful for setting up an early warning system?
Yes. So yeah, I want to show this figure if I can still show it.
Yeah, please do.
Yeah. So do you see this cartoon? Oh yeah, I go back to the cartoon pro. Okay. I did some calculation. Okay. So in order to have in order to be able to do a tsunami warning, it's really latency is a key. So I mentioned that it takes 8 minutes from the surface to the ionosphere for the sound wave. Okay, then you need to have a data processing time for the. So if you have a real time data for a ground-based GPS station, you still need to have a processing time. For example, you need to collect certain data to identify the signature. So if you add 8 minutes and identify processing time 10 minutes or 5 minutes, you are kind of like 8 minutes plus 10 minutes, 18 minutes. You need to have everything 18 minutes ahead of it. Then you need to consider the location. Okay. So I mean, to answer Professor Eve's question, is like it depends on how fast you can find the signature from your data and how the tsunami arrived. And then I mean, it's a trade-off in between the leading time and the latency for the ionosphere to feel the tsunami and for the time you need to processing the data. So I don't know how good we can do right now, how fast we can do right now. If we can build a system that can processing the data quicker, then the warning time will be longer. If not, then the warning time will be shorter. I hope this answers the question. Yeah.
So you think it's impossible?
It's possible. I mean, it's possible. I mean,
But how?
at the beginning, I think it's possible because if we find a system it's so 1 hour leading is so important. 8 minutes for the ionosphere to fill it, right? And then 10 minutes to process it. You spend 18 minutes, so you still have a 42 minutes to identify other things,
How long
and
does
then send up. Yeah.
how long does it take to transmit the data from the satellite to the data center?
Oh, I mean, it's not a data center; it's a receiver. So
Huh?
right now, all the research I show are the free launch receiver. So we need to wait for 2 days to get the data.
So it's
But if
delayed.
you No, no, no. But if you put a real time data, for example, right now in the world there are 400 real time data. If you have a real time data, then if the time delay is within minutes, you still be able to do that. Yeah, so you have to do the real-time data to be operational. So Professor, I'm talking about from research mode to operation, you know. So for the Cosmi one, the latency is 3 hours. For Cosmi two, data latency is 45 minutes. So from research to operation, it depends on how good you you reduce the latency in your operation system. If you can do that within 1 hour, then it's possible to do the warning. And
But
then this is the ground station for the CubeSat. Then it would be your question that how long does it take from the satellite to give the data to the ground station?
yeah,
For satellite, is your question will be for the satellite.
yeah. Okay, we have another question in the chat box. Merkin Turkman, can you ask Professor Lin the question, or you want him to read your question?
Sure. I was wondering. Hello, thank you for the presentation.
Yes,
Prof.
thank you.
I was wondering if these earthquake-produced irregularities always in large scale, and is there any like small, medium-scale irregularity coincides with an earthquake that gives more information
Yeah,
regarding?
I think yes, you're asking a very good question. So it's a little bit similar to the question Professor Wen-Yi asked, but it's in different perspective. So what Professor Wen-Yi asked is a processing time, latency, and leading time. Your question is can the earthquake signal or tsunami signal large enough to to overcome the other existing perturbations? I should tell you this: if the earthquake has a magnitude larger than 7.0, there are good chance we can find it, and we can easily distinguish it from any other ionosphere irregularities. However, if the earthquake is smaller than 7.0, we found it difficult to identify. That's for earthquake magnitude. For tsunami, I think we need to have at least way high of over 1 meter in way high, so that we can identify the signal. So the way to identify signal is there are many perspectives. For example, plasma bubble occur at nighttime, propagating only eastward. If we see something happen in daytime propagating westward, then it's not likely the ionosphere plasma bubble. So we can do something like this to using different, known feature of this TID, existing TID, to identify whether they are tsunami or earthquake effect or the normal ionosphere perturbations. But your question is very good because magnitude of earthquake, magnitude of tsunami is important. At the beginning, when we did this, we want to do this for all kind of a tsunami, all magnitude of a tsunami, but then we couldn't do it. Then we realized, okay, let's just keep up the small tsunami. Let's only handle the fatal events. So I think if we want to build I'm sorry, I speak longer because your question can prompt me with a good explanation. So I think by using ionosphere itself is insufficient. We need to have this coinciding with existing tsunami warning. So if both system tells you this one is huge, then this is a devastating, this is a fatal one. So something like that, we need to combine the system, not just only one system replace the other. It's just we need to have a combined system. That's what I want to also mention. Thank you for your question.
Thank you for a really good answer. Thank you, Prof.
So very good. Other questions from the audience? We see that when during the Q&A session, we have more participants than listeners at the beginning. So other questions to Professor Lin? And I see the names, Olive and Nona. And Nona, you have questions for Professor Lin? If not, I think we would end this talk now. But I want to tell you that in 2 weeks' time, there will be another talk given by Professor Dang-Suk Lim. Professor Lim, he's at the Washington University, St. Louis, and he is actually a mathematician. But he's interested in using his mathematical scheme methods to make the early warning system work. So it'll be very interesting for you, to participate, to listen to him, and see how he has some idea how you could make using machine learning, AI, and using mathematics to have a early warning network. Yeah, and we want to thank Professor Lin again. Thank you. Yeah, for a very nice
Thank you.
talk. Yeah,
Thank you.
thank you all for the participation. Thank you.
Thank you. Yeah, I'll be happy to interact with you, all of you. Thank you.
Right. Thank you. Bye bye.
Bye bye.